Hello, Intro to Chemistry class. Can you believe we made it to chapter 14 this week? That's pretty crazy. There's 16 chapters total in this class. So this week we're in chapter 14. The third exam will cover chapters 12, 13, 14, and 15. And then the final will cover chapter 16 the last week, and then the final will cover everything. So we're getting near the end here, aren't we? And you're doing good to hang in there. So let's just keep going. This week, we're going to learn about solutions. You've heard the term, we've used the term actually all the way since chapter 1. In chapter 1, we learned that a solution was the same thing as a homogeneous mixture. And we learned that homogeneous mixtures were the same when you had a mixture of two or more substances, and that mixture was the same throughout, meaning everything in the same phase. So everything was liquid, everything was solid, or everything was gas, but none of those different. So for instance, if you had a liquid and a solid, that would not be a homogeneous solution. They would not be dissolved into one another. So you wouldn't have a solution. So let's look at the definition of solution. Once again, it's a homogeneous mixture of one or more solutes and a solvent. So now we're introducing two new terms, the terms solute and solvent. When you refer to a solution, there are many parts, at least two, but perhaps more. The compound or the substance that does the dissolving, which is usually the one in the major amount, so the one that there's the most of, is called the solvent. So the solvent is the dissolving agent. If you were to dissolve salt into water, right, to make a saltwater solution, the water would be the solvent. It's the dissolving agent. Usually it's the one that's most abundant in the mixture. What if you put two liquids together, like ethanol, which is a liquid, and water? This is where most of your alcohol mixture comes from, actually. There's usually alcohol and water. Well, if you have two liquids together, the dissolving agent, or the solvent, is usually the one that's more abundant. So let's say I make a mixture of 50 milliliters of ethanol and 100 milliliters of water. Because they're both liquids, the water would be the solvent because it's in the greater amount. But if I had 100 milliliters of ethanol and only 50 milliliters of water, we would then call ethanol, that liquid, the solvent. So whenever your phases are the same, the solvent is the one that's most copious. All right, the solvent is the dissolving agent. What does it dissolve? It dissolves the other substance, the solute. And you can have more than one solute in a mixture. For instance, salt and water both dissolve in water. I could put some salt and some sugar in water. And the salt and sugar dissolve, so they would be the solutes, and the water again would be the solvent. So the solute is the substance being dissolved. Okay. What types of solutions can we have? That's a good question to ask. Are all solutions liquids? No. Solutions can be in any phase. It's just a homogeneous mixture, so everything's in the same phase. So think of solutions can either be in the gas phase, the liquid phase, or the solid phase. So what are some examples of gas phase solutions? One example is air. Air is a mixture of several different gases, the main component being nitrogen and then oxygen. We've got carbon dioxide, argon, some helium, etc., etc. All of these gases are uniform distributed mixture throughout. When you take in a breath of air, you don't have to worry about the oxygen content of that air from one side of the room to the other because it's the same throughout, right? So air is a homogeneous mixture of gases, or it's a solution of gases. You can also have liquid solutions. These are the type of solutions we've been using all semester. Like in lab, you'll notice we used hydrochloric acid. We usually use a solution of hydrochloric acid where it's dissolved in water. So that's a liquid solution. We used a lot of liquid solutions in our single replacements and double replacement lab, actually, where we had salts dissolved in water, ionic compounds. Now, what's an example of a solid solution? Solid solutions are a little bit difficult to kind of think about at first because solutions have to be homogeneous throughout. How do I get solids like copper and lead, or iron and copper, or iron and antimony, or any of these liquids, how do I get these solids to mix together and be uniform throughout? Well, usually when solid solutions are made, and solid solutions are called alloys. Have you ever heard of alloys of metals? Like bronze, iron is the main component, and steel. Steel is an alloy. It's a mixture of metals. How do you make alloys? Well, you actually mix the metals or the solids in their molten state, so in their hot liquid state. And when they're liquefied, you make the homogeneous solution, and then it will harden and temper down to its solid state, and that's where we get the alloy from. So an alloy is basically a solid solution. All right. So let's see here. How do you know if you have a solution? If you're going to be in the lab or you're looking at a mixture, how do you know you have a solution? Sometimes the word homogeneous mixture is not a very clear answer. So here's ways that you know you have a homogeneous mixture. Observations you can look for. And most of these will apply. I'll get to one there's an exception. But the first way that you know one characteristic of a solution is that the distribution of the particles in the solution is uniform. The distribution of the particles in the solution is uniform. That's basically what we meant by homogeneous mixture. The second way that you know that you have a solution is that the components of a solution do not separate upon standing. What do we mean by this? Well, let's say we have two liquids, oil and vinegar. You know that you can put oil and vinegar together to come up with oil vinaigrette type dressings, right? If you mix the oil and the vinegar, the two liquids together, you can put them in a bottle, cap it, shake, 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 shake. Everything instantaneously will look very homogeneous to your eye, or the same throughout. But if you sit there and let the mixture sit for a while, or let it stand, you'll see that it will separate. The oil will go on top, the vinegar will go on bottom. And this is because you have not made a homogeneous solution. Oil is different than vinegar. They're not like in their charge components. Oil is very hydrocarbon. It has no polarity in the compound or the molecules. Vinegar is very polar, so they don't mix very well. So they don't dissolve in one another, and they will separate upon standing. So if it separates upon standing, you do not have a solution. You have a heterogeneous mixture, not homogeneous. All right, let's look at the third one. A solution cannot be separated into its components by filtration. Basically, if you have any type of liquid where you've dissolved particles into it, for instance, and you've dissolved, if you run that solution or supposed solution through filter paper, for example, and you filter the solution, all of the particles should be less than a nanometer in size, and that's smaller than the pores of any filtration device. That means that you shouldn't be able to separate the solid portions, even the minutely particulate matters, particles, from the liquid. It all needs to be in the same phase. So if you can separate by filtration, that means there's small particulate matter or solid suspended in the liquid. When particle sizes get between 1 nanometer in size, that are the solute particles, to 10 nanometers, we are no longer in a solution phase. In fact, these are things called colloids. When the particles are not quite solids, but they're not quite all dissolved yet, they're kind of in the Brownian motion of sticking together phase, where they're kind of small but still large clumps of matter dissolved in the solution. We call those colloids. You've probably seen some colloids before. They're not technically solutions. For instance, have you ever driven around on a foggy morning? The fog that you drive through is an example of a colloid. You don't have liquid water in the air in the gas phase, right? So it's not technically liquid because it's not raining, but it's not and it's not solid either, but it's not completely in the gas phase. You have water molecules that are kind of larger in size, a few clumps together between 1 to 10 nanometers, and that's how you're able to see a little bit of that fog standing in the distance. So it's technically not a solution. So you cannot separate from filtration, or another way to say that all of the ions or molecules that are dissolved, the solute particles, have to be less than a nanometer in size. All right, number 4. For any given solvent-solute combination, it's possible to make solutions of many different compositions. What do I mean by this? You should be able to take a solute and a solvent and have several different concentrations of those solutions prepared. For example, if I had salt and water. So here I've got these beakers of water. Water, water, water. I could dissolve a little bit of salt in the water, or I could dissolve a lot of salt in the water, or I could dissolve a medium amount of salt in the water. Here I've made different compositions or different concentrations of the salt water, from very salty to hardly salty at all to moderately salty. The fact that you can make different concentrations of salt water tells you that perhaps you have a solution, because its concentration of the solute can vary. Another example of a solution, just to show you that you're probably familiar with the fact that you can make different concentrations of solutions. Coffee. You know that the amount of coffee grounds that you use to brew in a coffee can really drastically change the taste of coffee. I'm sure you've had coffee before that you thought was very weak. You could barely even taste it. It hardly had any of the tannins and flavonoids and any of the caffeine that were extracted out of the coffee beans actually in the coffee solution. So there was a lot of water and not much of the coffee taste. But then sometimes people use tons of grounds. Instead of maybe the 2 tablespoons that's suggested for serving, they'll use maybe a whole filter full. Like, some people just don't know how to make coffee, right? And it would be very strong. And the stronger it is, the more bitter it is, right? So the fact that you can have different concentrations of even coffee that you drink, coffee is a solution. It's a homogeneous mixture of all those different flavonoids and tannins and all those other extracts from the bean in the water layer. All right. Let's see what's next. Number 5. Number 5 says, solutions are almost always transparent. This is the one that has the exception. Solid solutions are the exception, because a solid solution, once again, do you remember what it's called? A solid solution is called an alloy. And solids you can't see through because there's no space between the particles and they're not moving. But solutions are almost always transparent. Remember, transparent is another word for clear. It means that the light refracts through the substance. So let's think about air. Is air transparent? Can you see through air to get to other things? Yes, you can. It's transparent. We don't see it. The light reflects through it, or basically goes through it. So air is a solution by that characteristic. Let's think about some of the solutions that we looked at in lab a few weeks ago when we were doing the double replacement lab. Remember when you observed the compounds before you, or the solutions before you poured them together, one of the observations you made time and time again was that whether or not the solution was colorless or not, or whether it had color, it was always transparent, which means the light refracted through the sample. It was clear, you would say. Now, clear, like I said, does not mean colorless. Solutions can have color. For instance, if you took water and food dyes, you could make different color solutions of food dye that were dissolved in that water. But you could see through them, or light would go through them. They'd be clear. Let's look at number 6 real quick. It says solutions can be separated into pure components. Separation is a physical change, not a chemical change. So if you have a solution you should be able to separate it into its components, the solute versus the solvent. However, that separation process is related to physical changes, not chemical changes. So not be a chemical reaction like changing electrons or redox reactions. An example of a physical change, remember once again we had the salt water solution. So here's my salt water. How in the world could I separate salt from water to get the pure components back out? How could I get salt separated from water? Well, one way to do this is to boil the water off. The process of boiling is a physical change because the water goes from the liquid state to the gas phase. And that's a phase change, which is a physical change. The boiling point's a physical property of water. And I can boil off the water and the salts remain behind. So that's just one example. If you have two liquids, for example, if you have ethanol and water, ethanol dissolved in water, ethanol has a different boiling point than water. So even though you have two different liquids and they both can boil, if you boil at the lower temperature, the temperature the ethanol boils at, the ethanol will boil off first, and then the water will be left behind. This is called a distillation. You might have heard of stills before, kind of if you're, I don't know, I'm from Kentucky. So if you don't know what a still is, you can look it up. But the process is a chemistry process called distillation, or the boiling off and collecting one liquid and from a different liquid using the boiling point differences. So these are the characteristics of solutions. You should be able to be familiar with these characteristics as we go through the chapter. So let's think about some terms that we're going to use in this chapter. We talked about the term solution. It means a homogeneous mixture, the same throughout, and we discussed the characteristics of a solution. And we said there's two parts to a solution. Every solution has a solute and a solvent. And we said that a solvent is the dissolving agent. It is what breaks apart or mixes up the solutes, depending on what we're talking about. And the solute is what's broken apart from the solvent. So when we talk from the solvent side, we use the word dissolves. The solvent is always dissolving something. The solute is always being dissolved. Another way we can say this is that a solute is soluble in the solvent. So we've used this term soluble before. Soluble means to be able to be mixed into a homogeneous solution, to be made into solution. So when any solvent or solute is soluble in a solvent, it's being able to be made into a solution. Let's talk about solubility now, because this is very similar to the word soluble, but it's solubility. Solubility is a property, a physical property of any reagent that can be listed. So it's just a physical property that's known of any compound or substance. What is the solubility? So the physical property tells us the maximum amount of solute that can dissolve in any given amount of solvent at a given temperature. Let's think about what this means. If I want to list the solubility of a substance, for example, the solubility of sodium chloride in water. The solubility of sodium chloride in water, if I look up that physical constant on a chart or a CRC or some kind of table, I'm going to get a number out of there. And that number will have units too, but it's going to tell me the maximum amount of solute that dissolves in a certain amount of solvent at a given temperature. So let's say that I have a substance and it dissolves, let's say, it dissolves 2 grams of the substance in every 10 milliliters of water. Okay, that, or maybe at 25 degrees Celsius. That would be an example of the type of data you're going to find in a solubility chart or a solubility table. If I divided this, you would see that I would get 0.2 grams per milliliter in water that substance would dissolve at 25 degrees Celsius. What we see here is that for solubility, there's a certain amount of solute that will go into solution, a certain amount of solvent, and the amount is dependent on the temperature at which you're dissolving. Solubility is temperature dependent. It's temperature dependent. It means that it will change with given temperatures. Some compounds, if you increase the temperature of the solvent, you will get higher solubility, or more will dissolve. This is true of like sugars and things like that. If you take water and you dissolve it if you take sugar, and dissolve it into room temperature water, you'll get a certain amount of sugar in the water. But if you increase that water to boiling, you will be able to dissolve much more sugar into the water. And the opposite is true of other compounds. For example, carbon dioxide. We know that we can dissolve carbon dioxide actually into water. We can make carbonic acid. At room temperature, carbon dioxide is more soluble in water, and if the water is boiling, the carbon dioxide is less soluble. And we'll talk about why that is later. But just know that solubility is a term, it's a physical constant. For every solute, it will have a certain maximum amount of solute that's going to be dissolved in that solvent, and it's temperature dependent at a different temperature. If a solute has really low solubility in a certain solvent, we say that the solute is insoluble in that solvent. For example, if you try to dissolve salt into vegetable oil, it's going to have a very, very, very low solubility. You might say that it's insoluble because on practical terms, hardly any or to no amount of that salt will dissolve. If you have higher solubility ranges where a copious amount dissolves, then you say that you are soluble. Just because a compound is soluble in a certain solvent, for instance, sodium chloride is soluble in water, that doesn't mean you can take as much sodium chloride as you want and put it in a certain limited amount of water and all of it will dissolve. Imagine taking half a cup of water. You can't put 3 cups of salt into half a cup of water and expect all of it to dissolve, right? That's just not going to happen. The water will only dissolve a maximum amount of solute. So solubility always has a limit. Whatever is past the solubility limit remains as a solid, if you're thinking about solids dissolved in liquids. So we use the terms soluble and insoluble to describe solids being mixed into liquids. Remember in lab we talked about a different term. We said that if a liquid is insoluble or unmixable inside of another liquid, we use the term immiscible. If 2 liquids are immiscible in one another, so a liquid with another liquid, one of those liquids is typically more dense than the other. So the more dense liquid will always be on bottom, and the less dense liquid will be on top. So if 2 liquids are not mixable or they don't form a homogeneous solution, you'll always get 2 layers, and this is their phase boundary. If the liquids, let's say one of them is colored and the other one's not. If the 2 liquids are miscible or they form a homogeneous solution when mixed, then you'll only see one phase. So we're going to do that in our solubility lab, so be looking for that. You'll be seeing that. If a compound is soluble in a solvent, there's 3 different types of solutions we can make as chemists. We can classify the solution that we make as either being a saturated solution, an unsaturated solution, or a supersaturated solution. So let's look at each of these. What does it mean to be a saturated solution? A saturated solution is a solution in which the solvent contains the maximum amount of solute that's dissolved at that temperature. So for instance, if the solute dissolves 0.2 grams per milliliter of that solvent at 25 degrees Celsius, the saturation limit is 0.2 grams per milliliter. If you put 0.2 grams in 1 milliliter, you have a saturated solution. What happens if you add more solutes to a solution that has as much solute as it can possibly dissolve in it? If you add a little bit more solute to that solution, it would not dissolve. It would just remain as a solid in the solution. And what is a solid called inside of a solution? It's called the precipitate. So it would just remain the solid, or it would be the precipitate. It would not dissolve in the solution. So if I have a saturated solution, it's got as much of the solute dissolved into the solution as possible. If I add any more solute, it will remain a solid at the bottom of the container if it's more dense, or at the top if it's less dense. It will not dissolve. What is an unsaturated solution then? An unsaturated solution is a solution that contains less than the maximum amount of solute that can be dissolved at that temperature. So once again, let's say that the solubility limit of the solute in the solvent is 0.2 grams per milliliter. If I only dissolve 0.1 gram into a milliliter of that solvent, I've not reached the saturation limit or the solubility for that solvent yet. So all of that would be dissolved, but the solution could hold more. So what would happen if I added a bit more solute to the solution? It would dissolve just a bit more. Like if I added 0.05 more, that would all dissolve because we haven't reached our saturation limit. In fact, I could dissolve up to 0.1 more, or up to 0.2, for example, and then anything I added after that, of course, would be solid still. All right, what is a supersaturated solution? I love supersaturated. A supersaturated solution is a solution that contains more than the solubility or the equilibrium amount of solutes that should dissolve at that temperature. What do I mean by this? Let's say that you go on a chart and you see that the solubility limit, or the solubility of a solute in solution, is 0.2 grams per milliliter. If your solution has all of the solute dissolved and you have 0.25 grams per milliliter dissolved at that temperature at 25 degrees Celsius, you have more than should be soluble in that solution. You would say that this was a supersaturated solution. It's holding more solute in the solution than it should be. These solutions are very unstable. If the solutions are disturbed in any way by shaking the container, or sneezing on the container, or dust falls the container, or you add a little bit of crystal, if it's disturbed in any way, usually these solutions will crash out, which means here, for instance, we have 0.05 grams of solute excess dissolved than should be. If I were to accidentally sneeze on the solution, let's say, or bump the table that the solution was sitting on, the excess solute that was dissolved in the solution would crash or precipitate out of the solution. Precipitate means to go from the liquid phase down to the solid phase. So it would precipitate out of the solution. And then you would just end up with a saturated solution again. So if we disturbed it, you'd go back to the saturated solution, 0.2 grams, and you'd have 0.05 grams of solid precipitated out. Okay, now how do you make a supersaturated solution? There's actually a trick to it. For many compounds, for many solutes, I should say, those solutes have different solubilities at different temperatures. For solids, usually you have a certain solubility at a certain temperature. But as the temperature, so maybe this is room temperature, and you'd have so many grams per milliliter, or grams per 100 milliliters. So here would be a point on the curve. At 25 degrees Celsius, maybe you're 0.2 grams. But as you increase the temperature, maybe to 30, maybe you'll get a little bit more in. And then you go to 35, you'll get a little bit more. 40, you'll get more. 45, you'll get more. So for most solids, as you increase the temperature, you increase the solubility, or the amount of solute that will dissolve into that solvent. so they increase. Well, what does this have to do with the supersaturated solution? If you're at a higher solubility at higher temperature and a lower solubility at lower temperature, what you usually do to make the solution is that you'll boil the solvent. While the solvent's hot or boiling, you'll add in copious amounts of that solute, and it will all be soluble. So you'll let it boil, and then while everything's homogeneous in the same mixture at that state, you'll let it cool. So you'll boil and you'll put in this much. As you let it cool, if you don't disturb it and you let it sit very still, all of the solute that was dissolved will be held in the solution as it gets cooler and cooler and cooler instead of crashing out. It's a very unstable solution though, so you have to be careful. So at a lower temperature, you'll be above the saturation limit. The curve here that I just showed, the solubility versus temperature curve, this line here that I drew represents the solubility limit or the saturation limit at each temperature. So if you're above this line, this is the saturation limit at each temperature, then you are a supersaturated solution. If you're below the line, you're an unsaturated solution. You could dissolve more. But if you're on the line, you're a saturated solution. You have the maximum amount of solvent that should dissolve at that temperature. So up here, if we have more, if we're in this supersaturated region right here, we have more solute dissolved than should at this temperature. We're supersaturated. So how do you make a supersaturated solution? Boil the solvent at the higher temperature, let it cool slowly. Everything will become suspended in the solution at that lower temperature until it's disturbed in any way, and it will crash back out to the solubility limit. Alright? So these are our three types of solutions we can make based on the solubility parameters of every solute-solvent combination at any temperature. We have saturated solutions, the most that can dissolve at that temperature. Unsaturated solutions, less than the maximum amount of solute that can dissolve. And we have supersaturated, more than the maximum amount is dissolved at that temperature.